13.8 billion years ago, there was no space, no time, no matter, no energy. And then, everything. All at once. How is that even possible? This is the single biggest question in all of science. We can trace every cause back to every effect, we can explain why stars burn and why planets orbit, we can predict eclipses centuries in advance and split atoms with precision. But the one thing we cannot explain is how the entire universe suddenly existed. And here's what makes it even stranger. Asking what came before the Big Bang might be a meaningless question, like asking what's north of the North Pole. Stephen Hawking proposed exactly this. If space and time are properties of the universe, then the universe's beginning was also the beginning of time itself. Before time, there could be no before. The geometry of space-time traced backward doesn't extend infinitely into the past. It curves around, rounds out, and simply ends. There is no edge to walk off. There is no moment before the first moment. Or perhaps there was no actual beginning at all. Some physicists argue our universe is just one bubble in an eternal, ever-inflating multiverse. While our inflation stopped after a fraction of a second, inflation continues elsewhere forever, spawning countless bubble universes throughout an everlasting cosmos. Others suggest we're living in the latest iteration of an infinite cycle. The Big Bounce theory proposes that universes expand, contract, crunch together, and explode outward again in an endless loop. No true beginning, no final end, just eternal repetition. Or maybe scale itself is an illusion. Roger Penrose believes the universe loses its sense of size at the infinitely small and infinitely large, making them equivalent, like how chess is played the same whether on a pocket board or spanning a courtyard. Or perhaps our cosmos emerged from colliding dimensions. Superstring theory imagines reality as 11-dimensional hyperspace, where our 3 dimensions of space and 1 of time are just a single brain in the overall bulk. Our universe's birth? Just higher dimensional membranes crashing together. Or perhaps there's something else, some corner of physics we haven't discovered yet, some equation we haven't written. But here's what we do know. 13.8 billion years ago the universe began, and this is the story of what happened next. In less time than it takes a photon to cross an atom, the entire observable universe went through more transformations than it has in the 13.8 billion years since. Forces unified and split apart, particles blinked in and out of existence. The fabric of space itself inflated by a factor of 10 to the 26th in less than a trillionth of a second. To understand how we got from nothing to everything, we need to zoom into the smallest fractions of a second and the largest scales of existence that human minds have ever contemplated. We're going to the Planck era. Where is the hottest place in the universe? The center of a star? 15 million degrees Celsius. Impressive, but no. A supernova? 100 billion degrees. Getting warmer. The hottest temperature ever recorded was 100 meters beneath snow-covered ground in Switzerland. In 2012, scientists at CERN's Large Hadron Collider smashed 2 lead atoms together at nearly the speed of light, creating a temperature of 5.5 trillion degrees Celsius, 50 times hotter than a supernova. And that's still nowhere close to the highest possible temperature. Temperature is just particle energy, how fast something vibrates. Absolute zero at minus 273 degrees Celsius is where particles would theoretically stop moving entirely, but there's also an upper limit, an absolute hot, where particles tear themselves apart from their own energy. It's called the Planck temperature, 1.4 times 10 to the 32 Kelvin.
Max Planck, the German physicist who founded quantum mechanics, realized there are fundamental limits to nature. Using the speed of light, the force of gravity, and his own Planck constant, he defined the smallest possible units of reality. The Planck length, 1.6 times 10 to the minus 35 meters, 100 quintillion times smaller than a proton. The Planck time, how long it takes light to cross that distance, 5.39 times 10 to the minus 44 seconds. These numbers are so extreme they're beyond human comprehension. We evolved to understand things at human scale, meters, seconds, kilograms. Not billions of billions of billions. But there's one moment in history when these units become essential. The very first instant of the universe. Because our universe is expanding, it was once smaller, much smaller. If we rewind time, the observable universe shrinks, becomes more compact, hotter, denser, until we reach a moment when everything we can see was exactly 1 Planck length across. 1 Planck unit of time old, at Planck temperature. This is the Planck era. 100 million trillion trillionths of a second after the beginning of time. And it is the strangest moment in cosmic history. Today, 4 fundamental forces govern reality: the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. The first 3 can be quantized, thought of as particles. Gluons carry the strong force, W and Z bosons carry the weak force, photons carry electromagnetism. But gravity is different. Einstein showed us gravity isn't really a force, it's the curvature of space-time itself, a warping in the fabric of reality. And this works brilliantly at large scales. We've tested it thousands of times, but at the scale of the Planck era, when the entire observable universe was smaller than a proton, general relativity breaks down completely. At those scales, quantum mechanics takes over, and quantum mechanics and general relativity are fundamentally incompatible. They give different answers. They contradict each other. So we need a quantum gravity, a theory that reconciles both. And we don't have one yet. To truly study gravity at these energies would require a particle accelerator the diameter of our entire solar system. We can theorize, we can calculate, but we cannot experiment. Some physicists propose gravity has a messenger particle, a graviton, like the other forces, but it would be essentially impossible to detect. Others suggest loop quantum gravity, where space-time itself is pixelated at the smallest scales, made of tiny loops instead of smooth curves. And then there's string theory. Particles aren't points, they're one-dimensional vibrating strings. Different vibrations equal different particles. But to make the math work, you need 10 or 11 dimensions, most of which are folded up inside the strings themselves. Each theory is more mind-bending than the last, almost impossible to visualize. And yet that's what we're trying to do when we imagine the Planck era. In the 1950s, physicist John Archibald Wheeler gave us the most tangible description: quantum foam. Because of Heisenberg's uncertainty principle, we can't define length, time, or energy precisely at Planck scales, so space-time itself becomes unpredictable, a bubbling, shifting foam where quantum micro-black holes and wormholes pop in and out of existence without cause or warning. For the briefest of moments, anything goes. But after just 100 million trillion trillionths of a second, the chaos ends. The universe expands, cools, minutely, and a new era begins, one where our current theories at least have a chance of describing what's happening. Because now the 4 fundamental forces that rule our lives today are about to emerge. But they won't appear all at once. They'll split apart in stages like a coin toss settling into heads or tails. Imagine flipping a coin. While it's spinning through the air, you can barely tell which side is which, it's just a blur. Heads and tails are indistinguishable. But the moment it lands, when all the energy is spent, the two faces separate. The choice is made. This is what happens to the fundamental forces at high energies. Increase the temperature dramatically, and the weak nuclear force and electromagnetism blur together into a single electroweak force. Increase it even higher, and the strong force joins them, creating the electro-strong force. This is grand unification. After the Planck era, for a period 10 million times longer, though still incomprehensibly brief, the universe was ruled by just 2 forces: gravity and the electro-strong. the entire cosmos was still smaller than a quark. Temperature 100,000 trillion Kelvin, a trillion times hotter than anything we've created in the Large Hadron Collider. This is the grand unification epoch, and it is absolute chaos. Photons spontaneously transform into matter-antimatter pairs, creating quarks and leptons. These particles decay back into photons almost instantly. Electrostrong bosons help quarks transform into leptons, leptons into quarks, matter into antimatter, and back again. Virtual particles, real particles, the line between them doesn't exist. Until 1 trillionth of a second after the Big Bang, temperatures drop to 1,000 trillion degrees Kelvin. The strong force breaks free. Two forces become three, and everything changes. But here's where we hit a wall. These theories describe particle behavior in the first moments brilliantly, but they don't explain the large-scale structure of the universe we see today. When we compare the starting conditions to the end result, the Big Bang appears broken. In July 2022, the James Webb Space Telescope sent back its first images from the deepest reaches of space, and scientists panicked. They saw galaxies, ordered, structured galaxies, just 200 million years after the Big Bang. Too early, too organized. Astrophysicist Alison Kirkpatrick wrote that she lay awake at 3 in the morning wondering if everything she'd ever done was wrong. Media outlets claimed Webb had disproved the Big Bang.
Thankfully, it was a false alarm. Kirkpatrick was worried about galaxy formation theories, not the Big Bang itself. We were missing a piece of the puzzle, not the whole picture. But the Big Bang does have 3 major problems that needed solving. And in 1979, one physicist figured it out. The average temperature of the universe in every direction is 2.7 Kelvin. Everywhere, across 93 billion light years. But if the universe has only been expanding for 14 billion years, how can 2 points more than 14 billion light years apart have the same temperature? They've never been in contact. Light hasn't had time to travel between them. Einstein's relativity tells us space-time can curve. If there's enough matter, it curves positively, like a sphere, and the universe eventually collapses in a big crunch. If there's too little, it curves negatively, like a saddle, and expands forever. But measurements show the universe is perfectly flat. The odds of this happening by chance? Like tossing a coin and having it land perfectly on its edge. Electrical charges exist in positive and negative pairs. Magnets have north and south poles, but while you can find lone electrical charges, a single proton, a single electron, you can never find a lone magnetic pole. They should exist according to our theories, but we've never found one anywhere in the cosmos. Alan Guth, pondering the monopole problem on a December night in 1979, realized something extraordinary. What if the universe didn't expand gradually, but inflated, almost instantaneously, to many times its size? Inflation proposes the universe doubled in size around 90 times in less than a trillionth of a second. Exponential expansion. Think of folding paper. Start with a sheet 1/10 of a millimeter thick. 1 fold, 2/10. 2 folds, 1/2 a millimeter. 7 folds, as thick as a notebook. 10 folds, as wide as your hand. 12 folds is the world record. A 1.2 kilometer sheet folded into a bundle 1/2 a meter thick. But keep going theoretically. 23 folds makes it a kilometer thick. 30 folds reaches space. 42 folds reaches the moon. 51 folds reaches the sun. 81 folds spans the Andromeda Galaxy, 141,000 light years across.
And 90 folds? Bigger than the entire Virgo supercluster, 130 million light-years across. This is what happened to the universe. In less than a trillionth of a second, it expanded by more than an octillion times. That's what put the bang in the Big Bang. The horizon problem? Inflation allows distant regions to have been in contact before inflating apart. They started with the same temperature, then were flung to opposite ends of the observable universe. The flatness problem? We might only see a tiny fraction of a much larger universe. Like seeing an ocean horizon. It looks flat, but we're standing on a sphere. The monopole problem? If monopoles existed before inflation, they were spread so far apart that there's roughly one per observable universe. In a sphere 93 billion light-years across? No wonder we haven't found it. Inflation coincides with the strong force breaking free during grand unification. The decay of electro-strong messenger particles created an inflation field carried by a particle called the inflaton. Quantum fluctuations, tiny irregularities, were instantly scaled up to massive proportions. These became the seeds for galaxies and clusters billions of years later. Inflation eventually stopped, we're not sure exactly why, and the inflaton field decayed, pouring energy back into the universe in a phase called reheating. The cosmos went from vast and empty to filled with matter and energy again. Now we're in the electroweak epoch, lasting until about a trillionth of a second after the Big Bang. There are quarks, leptons, matter, antimatter, ruled by gravity, the strong force, and the electroweak force. But there's still something crucial missing. Until particles have mass, they remain ungoverned by gravity. And that's where the Higgs field comes in. Imagine a crowded party. A normal person walks through the room easily, weaving between conversations. But when a celebrity arrives, everyone swarms them. Progress slows. They're surrounded, weighed down by attention. This is the best analogy we have for the Higgs field, and it won a bottle of champagne. In 1993, the UK science minister promised a prize for the best explanation of the Higgs field. Physicist David Miller won with this cocktail party description. The room full of people is the Higgs field. The celebrity is a particle gaining mass. The ripple of rumor passing through the crowd is the Higgs boson. In the 1960s, Peter Higgs proposed that particles started with no mass. Then, within the first split second, a new energy field emerged, permeating all of space-time, giving particles their mass. Different particles interact with the Higgs field differently. Photons and gluons? No interaction. They remain massless. Quarks and leptons? They gain mass according to their type. W and Z bosons? They become heavyweights, 40,000 times heavier than an up quark. The theory was sound, but finding the Higgs boson took 50 years. Scientists smashed particles together in the Tevatron in America and the Large Hadron Collider in Europe, searching through wreckage for years. The problem? Higgs never said what energy would produce the boson or what it would look like. Like searching for a needle in a haystack when you don't know what a needle is. In 2012, experiments at CERN finally found it. The Higgs boson exists. The Higgs field is real. A trillionth of a second after the Big Bang, the electroweak force catastrophically splits in two, ending the universe's perfect symmetry. The Higgs field emerges, imbuing particles with mass for the first time. The W and Z bosons become massive. Quarks and leptons gain mass. Photons and gluons stay massless. And by a billionth of a second after the Big Bang, the universe finally contains all the ingredients needed to make stars, planets, and us. The cosmos is filled with a primordial soup, a quark-gluon plasma. This is what everything will be made from. But temperatures are still too high for meaningful interaction. By a millionth of a second after the Big Bang, the universe cools to just 1 trillion degrees. Quarks finally slow down enough for gluons to bind them together. 3 quarks make a proton or neutron, composite particles called hadrons. But here's the strange part. Protons are mostly empty. 2 up quarks and 1 down quark account for only 9% of a proton's mass. The rest comes from energy, quantum dynamics, and virtual particles. As much as 99% of a proton is made of particles that don't really exist. At first, protons and neutrons keep swapping identities thanks to the weak force. But as temperatures drop below a certain threshold, around 1 second old, this switching stops. Hadrons choose an identity once and for all. And here's where fine-tuning saves the universe. Down quarks are slightly heavier than up quarks, so neutrons, 2 downs, 1 up, are slightly heavier than protons, 2 ups, 1 down. During freeze-out, it's easier to go from heavy neutron to lighter proton than vice versa, so we end up with about 7 protons for every neutron. Protons form hydrogen, fuel for stars, foundation for chemistry. If neutrons had been favored instead, the universe would be filled with inert helium and unreactive neutrons. No stars, no fusion, no chemistry, no life. We got lucky. But there's another imbalance, the mysterious lack of antimatter. Antimatter annihilates on contact with matter, releasing enormous energy. 1 gram of antimatter equals a nuclear bomb. In the beginning, matter and antimatter formed in equal pairs. They should have annihilated completely, leaving nothing but energy. But somehow, for every billion antimatter particles, there was 1 extra matter particle. That tiny imbalance is why anything exists at all. Around 1 second after the Big Bang, neutrinos, ghostly particles that barely interact with anything, break free from the dense cosmic soup. They stream through the universe, leaving an imprint. If we could detect this cosmic neutrino background, we'd see the universe at just 1 second old, 380,000 years earlier than the cosmic microwave background. By 10 seconds after the Big Bang, temperatures drop enough for deuterium nuclei, 1 proton, 1 neutron, to form. But they're unstable. Photons break them apart immediately. This is the deuterium bottleneck. Only after about 300 seconds, 5 minutes, do temperatures drop enough for stable deuterium. Then helium-3 forms, then helium-4. By 20 minutes after the Big Bang, the nuclear furnace dies. 4 elements exist: hydrogen, helium, lithium, and beryllium, though beryllium decays quickly. The universe is about 75% hydrogen, 25% helium by mass, and that ratio holds true 13.8 billion years later. This is primordial nucleosynthesis, and it's a stunning confirmation of Big Bang theory. Recombination, 380,000 years. For hundreds of thousands of years, the universe remains opaque. Photons are trapped, constantly colliding with free electrons and nuclei. But eventually, temperatures drop to about 3,000 Kelvin. Electrons slow down enough to be captured by nuclei, forming the first neutral atoms. Suddenly, photons can escape. They travel freely for the first time. What was opaque becomes transparent, what was plasma becomes gas. This is the cosmic microwave background, the first light of the universe. In 1964, 2 Bell Labs researchers, Arno Penzias and Robert Wilson, were trying to detect radio signals from intergalactic space. but they kept hearing persistent radio hiss from every direction. They cleared out pigeons and pigeon droppings from their antenna. The hiss remained. Turns out, they'd accidentally discovered the afterglow of the Big Bang. Light from 380,000 years after creation now stretched into microwave lengths by 13.8 billion years of expansion. They won the Nobel Prize. The cosmic microwave background is 2.7 degrees everywhere. But there are tiny variations, hot and cold spots differing by a few hundred thousandths of a degree. These variations are the seeds of galaxies. Denser regions attracted more matter, eventually triggering star formation within 100 million years.
Hidden in the CMB is another pattern, ripples from sound waves in the early plasma. Before atoms formed, gravity pulled matter inward, while photon pressure pushed outward, creating spherical ripples. When atoms formed, the ripples froze. They're now 500 million light-years across, a standard ruler for measuring cosmic expansion. But simulations using only normal matter don't create the universe we see. There aren't enough galaxies, star formation is too slow. Something's missing. Dark matter. Fritz Zwicky noticed it in 1933. Galaxies moving too fast for the visible matter to hold them together. Vera Rubin confirmed it in the 1970s. Stars at the edges of galaxies moving as fast as those at the center. Dark matter outweighs normal matter 6-to-1. It doesn't interact with light or the electromagnetic force. Only gravity. We can't see it, but we can see its effects. During the cosmic dark ages, before the first stars, dark matter clumped together faster than normal matter, creating gravity wells. Normal matter followed, forming filaments and nodes that became nurseries for stars and galaxies. Without dark matter, the universe would be a thin soup of hydrogen. No galaxies, no stars, no us. And then, about 5 billion years ago, shortly before our solar system formed, something changed. Astronomers studying distant supernovae noticed they're more redshifted than expected. The universe isn't just expanding, it's accelerating. We call this dark energy. It makes up 68% of the universe. We have no idea what it is. So here we are, 68% dark energy, 27% dark matter, and less than 5% normal matter. From these ingredients, following rules set in the first fractions of a second, the universe has grown for 13.8 billion years. Stars ignited, galaxies formed, heavy elements were forged in stellar furnaces and scattered by supernovae. Planets coalesced from dust, and on one unremarkable rocky world orbiting an average yellow star, chemistry became biology. Life emerged, evolved, became conscious. And now, 13.8 billion years after a moment that cannot be explained, we stand here, made of star stuff, asking the question that started it all. How did the universe begin? We may never have a complete answer, but every generation gets closer. Every telescope peers deeper. Every experiment probes stranger physics. And the fact that we can ask the question at all, the fact that the universe created beings capable of contemplating their own origin, might be the most remarkable thing of all. The universe's story doesn't end here. In fact, we're living in just the opening chapter. What happens next, the formation of the first stars, the death of galaxies, the ultimate fate of everything, that's a story for another time.